Hey friends, Bartosz, Roman,
Hi.
how's it going? Yes, I guess I'll start with one question and we will go straight to the talk. And the question is, as far as I understand, data-oriented design is an application, is an approach made for game development usually. So, Bartosz, why do you think this is something special or something useful for people building enterprise applications?
Well, there's this great divide currently between games and business applications. So when you, for example, see a business application which just has a bunch of controls and a bunch of business logic, what you usually find is that this application cannot even render animation and even like post state in a consistent frame rate. All the while, you have games like, for example, The Last of Us 2, which came out like last year, where the menu screen is rendered at 60 frames per second, and also it renders water physics and has like 1 million polygons and different sort of models, and all of these systems work interconnectedly without any issues. So I'm trying to sort of bridge this gap because business applications start like slow, they're like sluggish most of the time, and there shouldn't be like that, because that divide grows, and I want to like bring this gap, like make this smaller. That's why I think it's interesting to know why data-oriented design works in games and bring them to business applications as well.
Okay, got it. Thank you, Bartosz. So, Roman, at this point, I should ask you, so you came here because it's a new approach or because it's a performance issue?
Actually, I just was always curious about data-oriented design, so I knew something about it, I read something about it, but actually I never thought about it as about, I don't know, pattern to design business applications. And I worked with business applications a lot, so I know what is requirements for business and what business needs. And for me, it's quite hard to match these two things together. So just interesting for me to discuss with Bartosz how this thing could work in these business applications, what problems it could have, and so on, so on, so on. So just interesting topic for me to discuss. So we'd be happy to be here as an expert.
Okay, got it. So let's try to figure it out. Bartosz, giving the word to you. Let's go.
Okay, so hello everyone, and welcome to my lecture about data-oriented design for business applications. And this talk actually exists to bridge this gap that we've discussed before, but one of the interesting things that sort of happens when you try to apply data-oriented design for business applications is that there's not a lot of materials at all about this subject. What you'll usually find is that you will have a bunch of tutorials for like Unity game systems. So it's going to be like ECS architectures, which means entity component systems, which is not something that you usually want to have when you're starting like business development. You're not going to connect it to a game engine. So that's why this lecture is designed to actually give you some materials to work with data-oriented design for business applications. And another goal that I'm trying to sort of make here is that this should get you excited about data-oriented design, and you should like go and look for stuff, and you should try new stuff, and you should try to apply it in different sort of situations. So maybe it's going to provide you benefit. Okay, with that in mind, let's move to the agenda. So what are we going to be talking about today? So we're going to be talking a bit about me, because we do certain bits in like where I work, and we have data-oriented design in certain places. So then we're gonna ask a question: what really is DOD, and how does it compare to a more classical approach, which is like the object-oriented modeling or object-oriented design? We're gonna move to an interesting example, how structuring your data and like actually accessing your data can make a big difference. And finally, we're going to move to certain bits around processor and cache. We're going to discuss different sort of DOD patterns, not all of them, because there's a lot of patterns. And finally, we're going to move to a real world business example that we had to sort of solve the problem, and we solved the problem using data-oriented design. So we're going to start with a more object-oriented application like parser, and then we're going to try to refactor it to be more in line with the data-oriented approach. So this talk will not really cover entity component systems, but because it's like entry-level talk, but you can sort of find this information on your own if you'd like. We're gonna just touch on them, but not too deep, because that's like a 10-hour talk. So let's move. So I'm an R&I director, which stands for Research and Innovation. I work in SDI Media. I'm managing research teams, which means that I'm managing like computer science teams and data science teams. I'm a performance freak. I do code frequently. And what we're trying to build there, amongst other many applications, is a mass scale index for files, where we do a lot of parsing, statistics, data collection, and what have you, right? So this is like a fake screen from our application. You can see a bunch of files, and they have different extensions. So what we typically do is we index them, we then open them, we analyze the content, we do a lot of like data crunching there. And we have to build a lot of different sort of parsers and a lot of different models to then use that information in creative ways. So as you might expect, we do have a lot of data, because this screenshot will tell you that we have like 47 million assets, but that's an old screenshot, and now we have like double or triple that even. And the total size of all of these assets is like gigantic. I don't even know what the number is. It's just huge. So this application really requires like going deep into the performance aspects, and we tend to use data-oriented design sparingly currently. We use a lot of object-oriented design, but it's not what you think. It's a really our architecture is really flat in a way. But we have some like bits and pieces where we start to employ data-oriented design, and we're starting to shift in that direction. So that's interesting. So let's maybe ask, what is data-oriented design? But before we do that, let's actually think, and let's try to answer what object-oriented design is, because object-oriented design focuses on modeling the world using objects. So what I mean by that, we have certain objects, they have certain data, and they have certain functionality. And what is really, really important in object-oriented design is the interaction between those objects, the relationships. So we're trying to model the world, or like solve the problem using all of these objects and the relationships. So that is the thing that you have to focus on when doing proper object-oriented design. While data-oriented design, on the other hand, tries just to solve the problem. So it will focus on the data and the algorithms that try to do something with the data, meaning solve the problem. So you can think about data-oriented design as having a piece of data and a transformation function, which will solve the problem. So the data will go to that function and it will get transformed somehow, thus solving our problem. So in this context, data dependency, alignment, memory access patterns are very crucial things in data-oriented design, and like data grouping as well. But this can lead to an increase in performance. It can actually have like really positive impact on performance if you do this correctly. And one of the other things that tends to happen is that if we apply the data-oriented approach correctly, our system is really it gets simplified, because we don't have to employ a lot of object-oriented design patterns, because they just don't work in this approach, and we have like a different approach to solving problems. And data-oriented design is really based in that regard on 3 principles. Like the data is not the problem domain, which means that we're trying to solve the problem head first. We don't think about anything else but just solving the problem, and we're trying to do it. We just have data and we're trying to use it somehow. Then we're trying to say that data is not about the structure and our abstraction. So that actually means that we're not trying to abstract things away. We're just trying to focus on the algorithm, focus on the data that goes in and goes out. That's pretty much it. Then the final piece of the puzzle is if the data changes, the algorithms will reflect that change. And that actually means that the algorithm is the most important thing. The data is here to sort of service the algorithm. And typically on the web, you're going to find this sort of sentence that will tell you that data-oriented design needs to correct information. So what does it mean? Well, it means that if you focus on the problem first, focus on the data without even like structuring it too much and abstracting away, then you're going to see that the problem sort of matured in your head and you know much more about the problem than you did before, and you can make the correct assumptions. So this is like an evolutionary process where you sort of first try to solve the problem without doing any abstractions, and then you try to sort of move pieces around because you know what the problem really is. And if the problem is complicated, which usually is, even if it seems simple, then this approach can lead to simplified systems because you know more about the problem. So let me now switch to an example to just get you excited about data-oriented design. And let's have the following program. So what we have here is two functions. And the first function is called rows. The second function is called columns. And in each of the functions, we do a single thing. We have a array, which tends to be, it isn't a two-dimensional array, it's a single-dimensional array, but it's a matrix that's flattened. And in the rows version, what we're going to do is we're going to go row by row and increment each value of that row. So each cell will be incremented once. And in the columns version, we're going to do the opposite. So we're going to load a column and increment each column once. And can you tell me which program will execute faster? So think about this, and we're gonna just run it and see which one is it really, right? So let's run the program and let's see which one is actually faster. So I'm gonna load the columns version first, and this is the entire function. So we have our array of rows and calls, and in the columns version, we're just gonna go through columns and increment them. In the rows version, we're going to do the opposite. So one important thing about this test and all other tests that will follow is that we're going to use this quick benchmark function that I wrote. It's a piece of framework that it's open source. You can get it for free. And we're not going to use benchmark.net, which is the state-of-the-art benchmarking tool for .NET. And the reason for this is that benchmark.net is very precise, but the precision has a cost. That cost means usually a program to execute benchmark takes roughly from a minute to a minute and a half. And that's a bit excessive in terms of this lecture. So what we're going to do is we're going to implement a simpler function which does the same things as benchmark.net, but it does so in less iterations, it's more simple, and it executes way faster. So it will do all of the good stuff that benchmark.net does, which is like the JIT compilation phase, warm-up phase. We're going to actually do a bunch of runs, then calculate the mean, standard deviation, and what have you, right? And we're going to measure like the previous run as well in order to have the correct results. It's not going to be as precise as benchmark.net, but that doesn't matter in this case because we're going to have orders of magnitudes of differences in performance in these examples. So that's just a heads up, and let's run the columns version first. I'm going to run this in release, of course, without a debugger attached. So we go through the warm-up phase. Now we're going to execute this 10 times, measure each of the execution, and then we're going to calculate the mean, like memory, standard deviation, and whatnot, right? So columns took 300 milliseconds. Well, okay, it's something, but we don't know how much time the rows version will take. So if we run the rows version now, well, as you can see, it's way, way faster. It actually takes around 38 milliseconds as compared to 300 milliseconds, which is like 8 times the performance. So why is that really happening? Because if you think about the memory and how it's structured, if we want to access a cell in the memory, that time should be constant, right? Well, it turns out it's not the full picture. And data alignment has actually an impact on this, right? But in order to be able to understand it, we have to sort of explain the processor and cache in a bit, because we're not going to explain the whole thing because it's very complicated, but we have to explain some things. So a typical processor currently is a multi-core processor. Sometimes if you have like multi-socket processors like NUMA, for example, it's even more complicated, but typically you're going to find a multi-core processors, which like 4 cores, maybe 8 nowadays, and each core will have its registers, execution units, and its own caches. Like L1, L2 are exclusive to a core most of the time, and we're going to have like L3, which is a shared cache. So we know that this thing like exists, which is called the cache. So let's maybe see how much the performance we sort of have from these certain components. So if we think about the CPU and the registers, that actually is almost free in a way. It takes like 1 cycle or even less. So a like move operation, which is like the copy from register to register, takes executes 2 per cycle. So it's less than a cycle. That depends on the operation, but it's very, very cheap, right? And now L1 cache will have around 3 cycles per operation. Then L2 is like 20 cycles plus, because it can vary by CPU. L3 will be something around 50, and main memory will be like 500. And if we had like a SSD here, that will be like 50,000 cycles or something like that. So it's like no contest. So what we're trying to do is we're trying to be in the cache as much as possible. And if we can, we try to be in memory, unfortunately, right? So a word about the cache. So a cache is actually composed of a bunch of sets, and within each set we have a thing that is called a cache line. So a cache line is typically 64 bytes, and it has like a bunch of metadata like valid flag and a tag flag in order to be able to find it in memory and in order to be able to figure out which sort of portion of the main memory it maps. So the cache maps the memory, and these are composed into sets, and these sets are actually the thing that sort of maps the bits of memory, right? And there's like 2 to the A lines per set and 2 to the S sets. So this is just to show you that there's like their powers of there's 2 to the power. So you're gonna have like 32 sets of 16 lines per set and things like that. But that's not as important right now. The most important bit is that you have to remember is that if you ask the CPU for 1 byte, you're going to get 64 because it's going to preload the entire cache line. And if you want to save, the same thing happens. That cache line will be saved in this sort of set here, and that's going to be it. So each time you operate on something, you operate in terms of cache lines, which is very important for our case here, right? So going back to that example, if we look at data access patterns, so in the rows like example, we just load up a row and move incrementing the values of that row. Whereas in the columns version, we load a column, we load the first value, then we sort of have to drop that row, get a next one, and so on, right? So this is our data access pattern that we're looking at here. And if we sort of try to explain this data access pattern in cache lines, then in the rows version, what's happening is that we load up a single value, which loads the entire cache line, by the way. So we have then all of our data is in cache, that whole line is in cache, and we can increment each value in that cache line. And then we load up another one and do the same thing. And CPUs are very smart beasts. They have a lot of speculative execution units, which is the branch predictor and the cache prefetcher. So the prefetcher will sort of try to predict if our data access pattern is predictable. If it is, if it's like linear, so we're like doing sequential reads through memory, then it will preload adjacent cache lines. So it might be that all of our array is in cache before we even ask for like that piece of data. So that's very good because the data access times, as you recall, is around from 3 to 20 cycles. So that's going to be very, very efficient. And now let's look at the columns version. So the columns version is actually not so performant because we're gonna load up a value. It's gonna load the cache line, but we're gonna throw it away because it's the next column is somewhere else. So we're gonna load up another one and we're gonna throw it away, and so on, right? So the prefetcher cannot really predict our pattern, although you might think it's simple, it's not for the prefetcher. And we're just wasting a lot of data that we sort of load and throw away. So that's why the performance takes a big hit. And I did a benchmark.net, so I'm going to do benchmark.net on slides because they take too much time. So in terms of like proper benchmarking, this is the result that I got from benchmark.net. The ROSE version takes around 300 milliseconds, and the calls is like way more. It's like 5 times slower. And the reality of the situation is, if you have this sort of unpredictable patterns and you're wasting cache lines all the time, the more data that you're going to have, the worse it's going to be. And it's not a linear correlation. It's actually worse. It's not linear in a way that the more data that you have, the worse it's going to be. So it's going to be, if you added more data, it would be like 10 times slower or even 50 times slower. So this is something to keep in mind, right? So let's now move to data-oriented design patterns, because we know that data access is very important and caches are very, very important. And we discussed at the beginning that data access, alignment, and all of these things are very important in data-oriented design terms. So let's see how data-oriented design differs to object-oriented design. So in object-oriented design, we typically find an object-oriented design graph like so. So we're going to have an interface, and we're going to have a implemented interface, and A will have a bunch of like references to B, for example, to C, and then to D, and D is for example, an abstract class. So someone is going to implement that, and that's going to be E. So this is your typical object design graph. And that means that typical object-oriented design graphs tend to be very deep and very wide as well. And in terms of memory and data layouts, as you can see, if I want to do something with E, for example, I have to go to A, then jump to D, and then jump to E. And as you can see, our data is fragmented because we're sort of like using pointers all the time. So it can be anywhere really, if we sort of allocate the data, and it can be moved by the garbage collection as well. So we have certain fragmentation, so we have to jump between these pointers. Our data access is not sequential, so we might lose on cycles doing cache and doing data access and doing like pointer chasing. So to make things more like concrete, for example, this would be our object-oriented design approach to transaction. So we're going to have a class called transaction. It's going to have a bunch of fields. It's going to have a bunch of functionality. So perhaps like a send function, maybe a isValid function that will return a Boolean. And it's going to have like a datetime object, which is non-standard datetime. So we just cannot use the built-in. We're going to have a certain transaction info. And that transaction info is going to have some other object called segment, for example. So in terms, again, of memory layout, this would look something like this. So in order to get the segment, we would need to start from the transaction, then go to transaction info, then move the pointer to segment info. So this is what we have to do in order to be able to access that. That's not always bad, by the way, but in terms of performance, that can take a hit. So you have to keep that in mind. And now let's see how the data-oriented design graph looks like. So most of the time, a lot of the times, data-oriented design graph will just have a single object. And if it doesn't have a single object, it will have these data bundles where we sort of combine B plus C and D plus D. And as you can see, these arrows are dashed. And they're dashed because we might decide to have a reference in A, or even we might decide to not have any references. So these objects in data-oriented design terms are referenced in a kind of a different way. So this is where, for example, entities and components can come into play, and we're going to see that in a minute. So compare that to object-oriented versus data-oriented. This data-oriented design graphs tend to be much more flat. in structure. Because what we're trying to do at the end of the day is we're trying to bundle data by certain functionality that we use all the time. That's why it happens. And now if we look at layouts, this is one of the possible layouts that we can have. So we're going to have our object A and then B plus C and D plus E. They're going to be like nicely laid out in a sequential fashion if we're trying to access all of them. And then we can just access them without doing any like complicated point and jumping, right? And in like, again, transaction terms, if we're trying to do something concrete, we might start with a struct and a bunch of fields, right? And typically I get asked when I do these presentations, well, why not properties? Because we used properties before and now we're going to use fields. And there's nothing inherently wrong with properties. Properties used to be bad, now they're not really bad, because it used to be that properties were just a lot of typing for nothing, because the getter and the setter didn't do anything. So we might just use fields, and fields were actually more performant than properties back in the day. But now .NET Core 5 and 3.1 actually introduced a lot of new features, so we can use those features. But in the data-oriented design terms, if you use a getter and the setter, it had better be doing something. So that's why we're sort of starting with fields, because they're more simple. And now if you use properties, you actually might get a certain performance benefits, but I'm not sure. So that's why. It's just to simplify stuff. So we can actually structure our data differently, because that was a very flat structure. And say that we want to just send a transaction. So we're mostly interested in sending a transaction, and the rest we don't really care about. We just care about for like display, which doesn't happen very often. So we can structure our data in such a way where we would have all of the information at the top level to just send the transaction. And then we would just create a bundle of data called transaction info and just put it someplace else. So that might be a struct or a class, depending if you want to have a pointer, or maybe you want to have it bundled all in this struct, right? Or you don't even need to have this info here, because if you're not completely uninterested in having this object, you can like get rid of this object and have a different means of accessing it if you need it. So this is called typically a hot cold split, because if we're sort of interested in just using a bunch of data and that data has to be hot in cache, then we have to like create this bundle of cold data, which we don't care about at all. And we have to like get rid of it in a way, in like layout, right? And to sort of, if we wanted to get rid of that transaction info, what we can do is we can do a technique called a structure of arrays. So now we're going to have a struct, which is called transactions, and our like top level information that we're sort of deeply care about, which is sending the transactions, will be an array, and the transaction info will be another array. So now we sort of can turn this into this entity component architecture in a way. It's like very, very simple. But it's a start, right? So now what we're going to have is we're going to have an ID, which is the index of that array. So if we just care about transactions, we can just access this one array. And if we just care about transaction infos, we can access those. And if we care about both, well, we get an index from somewhere and we access these two arrays, and that's pretty much it. So one of the things I would like to sort of correct, because typically if you see like struct of arrays, that pattern, that sort of name, because it's a pattern structure of arrays, that doesn't really mean that it's a struct in like .NET struct terms. That's not correct. You have to remember that this is C and C++ like domain, and structs can be on the stack, they can be on the heap. You can decide where a struct lives. A struct here is just used to say that it's a bundle of data. So what we really care about is that we have a array, and that array is like has bundled data. It doesn't have any pointers, so that data is like continuous, right? This is what we sort of mean by a struct of arrays. We don't mean like .NET struct, not at all. So that's one of the interesting things that that sort of happens, right? And we can like move this forward. So maybe we're sort of interested in sending and receiving the data, so we can have these like data bundles here as well. And this sort of thing is really, really helpful, because now we can sort of access that in a very, very interesting way, right? So let me sort of show you what the entity component architecture means. So it's not an entity component system yet. So if we wanted to sort of structure that in this sort of interesting way, we can create this like entity component. So we're going to have a struct which is like the ID. It doesn't have to have anything else. It could, but there's no point in this example here. And we're going to have a bunch of components that have like just a bunch of data. And then we're going to have a transaction, and that transaction is going to have that entity ID. So that's pretty much it. And we're going to have a thing called the component store, where we're going to have a function called getComponent, and we have to pass the ID. And depending on what we're sort of interested in, we can get the data from one array or the other. So this is like the most simple thing that you can do in order to be able to represent the entity and components. So now your transaction is just an ID, and everything else you just get from this sort of store. So you can treat it almost as an in-memory relationship database, because people sort of treat it like that all the time in games. And that's a good way to think about it. Of course, there's the ECS like architecture, which is very complicated. There's a lot of problems, and this, of course, is not the full thing that you have to do in order to like make this work. But that's like out of the scope of this presentation, because entity component systems are really big topic. But okay, let's go back. And in terms of like memory and data layout, this time around, if we have these transactions, what we're going to see is that it's like continuous in data. So if we want to just send a bunch of transactions, we have to like set our pointer here and just do a sequential read, and that's pretty much it. So if we're sort of interested in something else, we have to go like set the pointer in someplace else and just read. And if we're interested in the whole object, which doesn't happen like very frequently most of the time, well, we have this ID that I just showed you, and we can piece together the entire transaction. And that's how we sort of apply the struct of arrays pattern here. So in the transaction, there was a field which is called isDPD. DPD and transaction terms is like this, Dave's past due. It doesn't matter what it is, but it's a Boolean. And in data design, a Boolean is an anti-pattern. We don't use Booleans. We try to not use Booleans in data design. And you might think, well, why? What's the problem? The problem is that we sort of, it doesn't contain a lot of information. It's just one bit to represent 1 byte. So that's a lot of waste. And it gets better because it's not 1 byte most of the time. It's going to be 1 byte if our data is packed. And the compiler can pack it, but most compilers won't. And as it turns out, in a 64-bit system, like in 64-bit compilation, it might be 8 bytes. So now we're sort of training 1 bit for 8 bytes. And that's a lot of things that we have to trade, right? So in order to be able to prove that, let me move to another example, which will do the following. And this is something that you can test yourself without any sort of problems. So we have the struct here called the transaction. It has a bunch of fields, and it has this DPD Boolean field, right? And what we're going to do is we're going to create 2 transactions, transaction 1 and transaction 2. And it's just to be able to tell which is which. Because we're trying to see how many bytes there sort of is going to be allocated and where, right? So now what we're going to do is we're going to take the pointers to both of these, and then we're just going to display the addresses and the fields, and that's pretty much it. So let's just run this program and let's see what's going to happen. So as you can, let me get this. As you can see, we have our transaction here, and this is our Boolean field. It's set to true, which means 1. So this ends at A0. And the next object starts at a 8, which means that we sort of padded this 1 bit to 8 bytes because the next object starts immediately after it. So that means it took a lot of space, and it's like for nothing, right? So that's why we don't use booleans. And it might be not so bad, because if you have a bunch of booleans, like a couple, and you add a couple of booleans here and here, what you're gonna see is this phenomenon called packing. So now the compiler has packed these bools. So again, this is padded to 8 bytes again, but this time around, this boolean, these 3 booleans are actually represented here, and it's just bits set within specific bytes. So now that's better, right? Well, not exactly, because you have to think about the problem that sometimes the compiler will pack it, sometimes it will not pack it. It depends on the data alone. The other problem is that if you're trying to be clever and use like field offsets and use like non-standard packing, it may not pack it at all. It might be a problem. So what we tend to do in the data-oriented design is we're trying to fold these bools into other fields. So perhaps these 3 booleans will be like folded into a int. So we would have like a field called state, and all of these will be folded into this one field called state. And we could use like bit manipulation tricks to extract the correct state, and that would be it. Or we can use an enum, for example, as well. So this is how we sort of do it in the like data-oriented design world. All right, so let's move to a real-world example this time around. And again, recalling our application here, like I said, we have a bunch of these file types, and we have to do a lot of things with these file types, answer different sort of questions from users, because that search box can answer questions as well. One of the files that we tend to parse is a PO file, which is a transaction file. And that transaction file has a bunch of transactions in it. And this is the schema. So the schema is it's a plain text file which has this sort of schema where we're going to have the ID field here, then we're going to have a Boolean field here which says that this transaction is like VIP, special, and whatnot. Then we're going to have the transaction state, non-standard date time, just cannot use date time here. And this is the amount field. And finally, we're going to have a node field, and the whole thing is going to be separated by a single empty line. And we're going to have a bunch of these transactions. So in our line of work, what we're trying to do is parse this file and answer a couple of questions. So the first question that we're trying to answer is, given a group of transactions from a client, what's the total amount? So we're trying to sum over the amount field. And the other thing that we're trying to do, which is the interesting bit in terms of like business applications, is we're trying to analyze this node here. That means we're going to do some NLP on it. And that ultimately means that we have to sort of figure out how to use like data-oriented design in the context of parsing text. And if you look on the web, you're not going to find almost any materials how to deal with large applications or large games which do a lot of text crunching, and this is what we're trying to do. So this is an interesting example, and we're gonna do 2 things here. First of all, we're gonna normalize this, so we're gonna do to lower, and the second thing that we're gonna do is we're gonna split this. So you might imagine that we have to handle text somehow. And text is non-trivial because it's a string, it has a pointer, it has all sorts of problems. So, sorry, we're going to have to sort of come up with an idea. All right, so what we're going to do now is we're going to start with the most simple thing that a newcomer could do when presented with such a problem. So we know what the schema is already, and if we know what the schema is, then the thing that we're going to do is we're going to resort to a regular expression parser, because that's the simplest thing that I can think of, right? So we're going to have a regular expression, and it's all good, and we're going to create this object here, like PO, object-oriented, which has a bunch of properties and a bunch of fields, and that's pretty much it. and we're gonna run it and we're gonna see how it behaves. So the first thing that we're gonna do is we're gonna sum over the amount using this parser. So this is the thing that we're gonna measure, mind you. So we're not gonna measure the parsing performance yet. We're gonna do this at the end, but first we're just trying to measure this bit here. And this bit is just summing over the amount and displaying the amount, and that's it. Done deal, right? So let's run it and let's see what the performance is. So the performance is around 360 milliseconds. So we don't know if it's good or bad yet because we have to run something else. But the second bit that we can do is to resort to a different sort of parser. That's a state parser, like object-oriented parser, but it has like this nice state. So we can sort of rewrite that because regular expressions can bite us in all sorts of creative ways that I don't even know about. And if we're gonna do it, let's do it the object-oriented way, but like object-oriented way proper. So we're gonna create a state transition parser. So the state transition parser will use exactly the same object, but it will go through like states, right? So if we run it now, unsurprisingly, probably there's not going to be a huge difference in performance because we have the same memory layout. Given that the regular expression parsing can do much more data fragmentation, it's not going to be a bigger of a difference, as you can see from the previous run, right? It is faster, but it's like 10% faster. So not much differences, right? But okay, now let's move to a more data-oriented design approach. So we can take the object and we can turn it into a struct, first of all, and second of all, let's just bundle every single piece of data here, and that bundle is, it's going to be a very flat object, right? So having that, we're not going to create like datetime classes, we're not going to create any classes, it's just going to be a very flat object. And let's just run this code and see if we get better performance of summing over the amount field. It seems to be very slow. Well, yeah, it is very slow, right? So it turns out that just converting this to a struct, flattening out all of the objects into like single pieces of data is actually slower. So maybe that's not the correct way to sort of refactor that, right? So let's maybe turn it into a something else. So now maybe let's do like a data grouping. So we're going to have this struct now called PO line data group, where we're just interested in the amount. So we're going to place the amount here, and we're going to create two objects that we don't really care about, called like PO state and PO date time. They're going to be classes because we want them to be pointers. We want them to be pointing to something else. We can actually get rid of them, but they're going to stay for now, right? And the reason why we have a struct is another class is that if we have an array or a list of structs, then they're going to be nicely laid out in memory. They're not going to create pointers. But we already saw that the performance wasn't really great, right? So something is happening, which is not good. And as you can probably tell in this example as well, the performance got better, but it didn't get better than the object-oriented version. So let's continue refactoring. So now let's use the hot-cold split. So the hot-cold split means that, well, if we're trying to do just sum over at the amount currently, let's just not care about anything else, and let's just leave the amount here, and let's make it into a pointer and forget about everything else, right? So now we have a single field here. So that should be good, right? Knowing that all of the things that we know so far. So let's run it, and as you can tell, it is faster. It's way, way faster. Now it's in line with the object-oriented version, which is kind of not really good. because it should be way, way faster. So what's the problem here? And I sort of baited you into thinking that this is slower because it's not. So let's go back to the first example that we did in like the data-oriented design. And what we're going to see here in this object here, that we went from a class to a struct. And that's pretty good. That's awesome, right? But let's now look at the code that does this, like the sum. It's a for each loop over a list. And that has a numerator, which is a struct, which has a method, and that method returns a struct, and that struct will get defensively copied. Not very cool, because right now, what really is happening is, well, we copy a lot of stuff. That's why it's very slow. So we can fix this problem by not copying stuff and not using a for each loop, but instead just using a for loop. And while we're doing that, let's not use lists, because lists tend to expand, they tend to double, but we don't control that pretty much. So, and if we're dealing with structs, these objects are already initialized to a default value. So maybe let's not do that. Let's switch to a different data structure called array, because that's more simple to do. And let's see how we perform. So I have a bunch of like fixes here. So let's see the state machine fix. So now we're using the for loop and we're accessing that directly. And we also have a variable called the index, because if we're going to initialize a big array that's bigger than the amount of like transactions that we find, we have to know where to stop. And this variable here will tell us where we actually stopped parsing, at which row. So this is the final real index of the array, right? So when we do that, then we can sort of measure the performance correctly. So let's run it. And now, as you can see, like the flat version takes 200 milliseconds. The object-oriented version took around 370. So it was in line with the previous run that we did. So now it's way, way, way better. And let's continue. So this is the flat data. This is the like data grouping that we did. So we grouped data into like these data bundles. And this is even faster, but like slightly faster. And the final one is, well, if we just try to sum over the amount, let's just leave the amount and let's get rid of everything else. Let's pack it into a class and forget about this, right? And this version actually is slightly faster again, but it's in line with the previous one. Okay, so as you can see, we're faster. So just to be extra sure, let's check the object-oriented version with the data-oriented version. Now, so this is our object-oriented version, and this is our data-oriented version. So as you can see, it's like 50% faster, almost 60% faster, just like that, right? So, and again, this scales with sizes and things like that. But now the really interesting thing that sort of happened, if we're going to look at data-oriented approach, we already know that it's faster. We can use the struct of arrays pattern. So let's refactor this again, and let's use the struct of arrays. So now our struct will look like this. So we're going to have a bunch of arrays representing different sort of objects. And one additional thing that we did is we got rid of the Boolean and we folded in the Boolean into a field called state. So we already had a field called state, but the state is a decimal. It can represent a lot of states. So that's how we did it. And now we have to initialize with a size. This, of course, can be like dynamic. We can implement a dynamic array here. Currently, it's static, but you can imagine that it's not very hard to expand this, because there's many techniques to sort of do expansion if it's needed. So the rest stays the same, and this is the only change. So now, if we want to sum over the amount, we just open this array, and we just go and do a sequential read over this array, and that's pretty much it for this particular problem. So let's run this. And unsurprisingly, this is the fastest version possible. It's like only 65 milliseconds. The object-oriented version is 300 milliseconds, so it's like almost 5 times faster currently. And as you can see, the other thing that tends to happen, and it happened in this case, the standard deviation is next to nothing. So there's not going to be a lot of like moving parts that can increase the standard deviation, because we may be like experiencing like garbage collection and things like that. So in this version is just in general more stable, which is a nice thing to have. And now, if we want to really go fast using this approach, because this approach on its own is already like fast by default. So if you have this structure, you're gonna see that it's pretty darn fast. But now we unlocked something. So we can now take this struct and we can use SIMD instructions to make it even faster, because now we're operating on a very simple type. Before we had these like structures or even objects, and for SIMD scenarios, this is like not the best thing that we can do, because if we're trying to sum over something using SIMD instructions, what we have to provide is we have to provide a pointer, and that pointer is going to get loaded into vectors. So if you don't know what SIMD is, it's single instruction multiple data. So it will do a lot of things at the same time. So we're gonna do a single instruction, and we're gonna do like 5 additions for that cost, right? So that's very beneficial, that's very cool, but the problem is that in order to be able to load up the vectors that we have to operate on, what we have to provide is a pointer. And we can pass a pointer to a struct, but if that struct contains like references, that's not so trivial. It is still possible. It is still possible to point to like pass a class, but it's almost at the verge of hacking the .NET. So I would not recommend that if you don't have to. And another thing that is really nice when you have the SOA approach, which is struct of arrays, is that if you think about SIMD instructions, you have to sort of realize that in order for them to be very efficient, you have to load the data into these 128-bit vectors as fast as possible. So your data layouts matter here very, very much. So let's just run this code. I'm not going to discuss how it's made. It's a very simple sum. It's not something that you just cannot find anywhere on the web, because if you do like C# in the tutorial, this is going to come up. So yeah, let's just run it. And it takes 40 milliseconds, so it's even faster. And as you can see, we went down from like 400 milliseconds to 40 milliseconds, just to sum over the amount. So that is a very big difference in performance. Okay, but let's now move to our second problem, which is even more interesting. So let's say that we want to do a split. So in our object-oriented design version of the parser and our object, we have this node field. And what we want to do with this node is we want to split this into words and perhaps do something with it. But as you may know, a string is an array of characters, and this is a pointer. So what tends to happen here is that in the object-oriented version, we have to go through each of the nodes in the line and just call split. And that's going to create a bunch of like other structures that we may, like internal structures that we may not want to deal with, who knows. But let's see how it performs. So let's go. And it takes 400 milliseconds and a bunch of memory. And this is to be expected because we're just creating a lot of strings, right? So 400 milliseconds. Okay. So how we would deal with this in a more data-oriented approach, perhaps using structs of arrays. So we're gonna have our initial struct that like we did before with ID, amount, and all other fields, but now we're going to do something different. Instead of having like an array of nodes, what we're going to do is we're going to create a string builder, which is a continuous memory block, but not really, because a string builder is a linked list data structure with memory blocks. But you can imagine that I didn't want to create like very complex data structures for this talk. You can imagine that it's kind of a continuous block. If you want to create a continuous block, you can do something else than a string builder, right? But now what we're going to do is we're going to create another array called a node offset. So now what we sort of have is all of our nodes are in this single big memory block, and we know where to cut them. And this array of nodes will tell us. So that's the only change that we had to do. And now if we're trying to sort of split them by words, what we're going to do is we're going to go to lines.allNodes, because we have all nodes in the same place, and we're going to split them. So if we want to have individual blocks, then we use the nodes array, but if we want just to split all of them, we can do a single split. And let's measure the performance for this approach. And unsurprisingly, it is faster. It's actually 2 times faster. And probably will consume a bit less memory as well. All right, so now let's deal with the final problem, because we want to normalize that string. So what we wanted to do in the object-oriented version is we want to take the node and we want to call toLower on it, because that is interesting to us as well. So we want to have like all nodes and we want to call toLower on them. And that's pretty much it. So again, let's run the object-oriented version. And this takes a bunch of like memory. Again, the mean is 500 milliseconds. And using our approach from before, we have the all nodes field, and we're going to do toLower on it. And again, it is around 50% faster. So this approach works really nicely. And again, having the like struct of arrays, and now we have a single like continuous buffer, we can do a toLower operation using SIMD instructions again, because we have a single big block of memory. That's our single string. So now we can again implement a function using SIMD instructions to be able to do like splits and toLowers and everything else that we can imagine. So it's very beneficial if you have continuous buffers of things, right? That's why the struct of arrays is very important in like the SIMD context. And unsurprisingly, it's very, very fast. It's like 3 times faster than the fastest version of the data-oriented toLower approach. And that's pretty much it. And let's move to benchmark.net this time around to see the results. So we started with a like regular expression parser, and it took around 30-ish milliseconds for like 10,000 samples. So this is like using different sort of sample amounts than we had before. But this is what we started with, and the struct of arrays is around 8 milliseconds. So all of these like approaches, the data-oriented approaches, are consistent in this example. If we would have more data, then probably that would be a bit faster. And of course, the SIMD instructions takes like 4 milliseconds, which is 10 times the performance. And when we're trying to discuss like parsers, so in this example, we're gonna see the performance of actually parsing the thing and doing the sum. So now we actually measure how like performant is the parser itself when our file is in the cache. So our file gets like preloaded into memory, and we're just testing how much time it takes to parse. So as you can see, regular expressions is the slowest, which is unsurprising. Then we have the data-oriented version, And the SIMD version, again, 40 milliseconds, but struct of arrays, 9 milliseconds. So that approach, again, people like to call it like fast by default. So that's really, really good, really, really fast. Hot code split. So if you're doing these like bundles of data that you work on frequently and unfrequently, that's really fast as well. So that's all for this lecture, and I hope this will interest you, and you're gonna try and apply these practices from the data-oriented approach yourself. And perhaps in a bit, we're gonna do another one discussing entity component systems and how to use them in business applications as well. So thank you, and you can, if you want to know more, not just about data-oriented design approach, but like different sort of things from computer science, performance, you can follow me on social media. You can read my blog. I have a lot of like computer science stuff on YouTube if that's your thing. So yeah, that's all for today, and thank you. It was a pleasure.
Thanks for your talk. I don't know if you're waiting to respond or not. Anyway, we don't have questions in chat right now, so I'm asking to anyone who wants to ask something, please just write it in chat. But I have a couple of topics to discuss from me. So my first question was right from the beginning of the talk, when you said that code would be simpler because we are not using some common OOP concepts, because it just won't work in this case. So all these concepts are mostly needed to make code much easier to extend, to modify, and so on. So my question is how hard it is to modify or extend code in data-oriented manner.
I haven't found it to be a very big problem because this whole thing is like we're trying to focus on an algorithm, so we don't have a lot of abstractions on top of other abstractions. So what tends to happen is we can change code freely, and if the algorithm itself is like intact most of the time, then it's not a big problem.
But what if algorithm is updated or data structure?
So if we update an algorithm, then we update the data structure, and that's pretty much it. If we change the algorithm, then we have to sort of rewrite this piece from scratch. But like we went from a regular expression parser to like a data-oriented design parser, and that structure changed all the time, and the parser got updated all the time, and that wasn't really a big problem. Not really.
Okay, that's nice. Okay, here's a question from chat. Will the sample code be available? It would be nice for me to walk it through.
I mean, it's already available, but not this version, and I'm going to make this version public as well.
Oh, okay.
So I'm gonna I can like give you hold on. Let me share screens again. Let me go here, GitHub. So I'm gonna share the code here. You can already see that there is a data-oriented design repo which contains a lot of the things that we sort of talk about here. So it's B. Adamczewski data-oriented design, but it's not the same version. This actually has much more stuff. It has like enumerable ref, bit operations, block lists, cache sizes. So it will like measure when we fall off the cache and whatnot. It's a different sort of version, but this version from this talk might be beneficial as well. So I'm going to probably create another repo somewhere here to house this talk specifically.
Mm-hmm. Okay, that's great. And I see there is some question from Konrad Kokosa, but he didn't finish yet. So, okay, another question from me. Mm-hmm. How hard it is for new developers to understand such a code wrote in this manner? So, for example, you hire something who don't have experience in data-oriented stuff.
So that's a very tricky question, and it depends on what your background is. So, for example, if you're a new developer on the team, and this happened to us a couple of times already, where you have like you're a very big proponent of the object-oriented mindset, then it's very difficult to sort of like switch because it's a like completely opposite. So you like created relationships between objects, and you're not going to do it now. You try to like prevent problems from happening, like even if they're like you try to like predict what's going to happen and prevent that in your code, you're not going to do it now. But if you're like newcomer from like university, then it's kind of easy, because like data-oriented design programming like stems from the roots of just doing like regular programming. So if you weren't exposed to this sort of corporate enterprise programming, that's easy. But if you were, then it takes some time to get used to.
Okay. And the question from Conrad. Nice talk, not data-oriented question related, but have you benchmarked regex-based version on .NET Core 3.1 versus .NET 5? Because .NET 5 brings so many regex performance improvements.
I didn't. I'm gonna bet that it's not gonna be faster than the SIMD version. I can tell you that. It's not gonna be faster than the object-oriented version as well. I know that they did a lot. They use like buffers and whatnot, but it all boils down to the regular expressions compiler. So if that compiler got improved, then that's good. But I can absolutely find more complicated state machines that the parser is not going to be able to handle correctly, and you can sort of tell why, because if you think about it, you have to use program synthesis to generate a piece of code that will solve your problem, and the engine to generate that is general, and your problem is very specific. So you're never going to beat like code that's very specific to handle just this one problem. It might be faster, but I'm not sure how much.
Okay. By the way, did you have your demos on .NET 5 or on .NET 3? .NET Core 3?
Let me check. I believe it's 3.1.
Okay.
But it is, where's the flag? 3.1, yeah. This one was on 3.1.
Because I just finished writing an article on .NET 5, and I found out how much performance improvements was there. By the way, have you seen it? What do you think about .NET 5 performance improvements and .NET 5 in general?
.NET 5 has a lot of interesting stuff made in terms of like JIT compilation performance. All of the oddities that were in 3.1 are mostly gone. There's still a lot of things to improve, but that code is way better. One of the interesting stuff that they implement in .NET 5, and it's just in its infancy stages, and that's very important to note, is the profile guided optimization. So for example, a profile will be created in like tier 0 compilation, and when we switch from 0 to 1, that profile is going to be used, which means that, for example, guided branch optimization can be possible. And I believe that's all of the things right now that the profile is used for, but it's a step in the right direction. So a lot of things got improved. For example, folding got improved in the compiler. Certain things around like division got improved because they sort of used a lot of the tricks that LLVM used when like compiling code as well. So it's a step in the right direction, certainly. So yeah, it is cool.
Okay. How do you think, is there a chance that your demos with OOP version would work, I don't know, significantly faster with .NET 5 or not? Just curious.
I'm not sure. We can check. Oh, wait. Oh, yeah. Let's go to version 1. Let's do the notes maybe. No, the notes are interesting. So this is the notes. What's going to happen? Uh, 377. The last version had around 500, so it is an improvement. But now let's move to DOD. $267, 40% faster still. And let's move to lower, because that got a lot of improvements around spans and memory and whatnot. 500. Okay. And DOD version. So the thing is that if the JIT compilation got a lot of love, it's going to like reflect this in the data-oriented version and in the object-oriented version. So both versions will be faster. So I'm not expecting to like be surprised, because I'm not currently. Yeah, 140, 124. Yeah. So both versions are faster, and that's awesome.
Yeah, that's actually great. Just because when I seen all the performance improvements in .NET 5, I was quite amazed. That was a great result.
So like I said, they're doing a lot of stuff in the right direction. What I would like them to do still is to have a like non-JIT compilation. So the JIT will, a compilation mode where the JIT will be turned off, and all of the optimization could be applied, because the problem with the JIT is that it has a very little time to do optimizations, so it tends not to do the very complicated optimizations. What it does, it's very simple arithmetic optimizations most of the time. And if you had unlimited time to do a release build, like for example C++, plus the profile guided optimizations, which LLVM has around like pointer chasing as well, then you could say, for example, that in .NET 6 maybe, or 7, who knows? I'm going to use JIT for like debugging. If I don't care about performance, I can have a release build with the JIT as well. That's cool. But now I can sort of wait 4 hours for my like super optimized release build. I don't care. Like do 100 optimization passes. Just do it.
That's great. I guess we're done with the talk, and we could slowly move to Zoom conference.
That's right.
For discussion.
That's the reason I'm here, actually. So I've just checked if my microphone is on. I just wanted to say thank you, Bartosz, and thank you, Roman, for your questions, and Bartosz for your talk. That was actually awesome. I guess that if you make some more ideas for benchmarking, you can continue it in Zoom. So the link to the Zoom, if you are watching us, is under Bartosz, and it's also in the Telegram chat.